Welcome to Chapter 2 of KIN 377, the measurement of motor performance. In Chapter 1, we built the conceptual scaffolding, actions, movements, neuromotor processes, and the 3 classification systems. In Chapter 2, we put that scaffolding to work by learning how to actually measure motor performance. Here's why this matters. Every concept in this course and every assessment you'll do in your future career depends on choosing the right measure for the right question. A PE teacher counting baskets, a coach timing a sprint, a physical therapist tracking stride length, a dance teacher reading a phase plot of a partnering lift, all of that is measurement. And getting it right is the difference between guessing and knowing. The chapter has 8 learning objectives, which I've grouped into 3 mini lectures. Take a moment to read the objectives on the right. These are exactly what you should be able to do when this is over. Pause if you need to. Ready? Let's go. Part 1. We're going to cover the first 3 objectives together because they fit naturally. Objective 1. Distinguish performance outcome measures from performance production measures, with examples of each. Objective 2. Describe simple, choice, and discrimination RT situations. Objective 3. Describe error measures for 1-dimension, 2-dimension, and continuous accuracy. Everything in Part 1 is on the outcome side of the chapter, the family of measures that tells us about the result of a performance. We'll start with the 2-category framework, look at reaction time as the most used outcome score, then move into the error measures, AE, CE, VE for 1-dimension, RE for 2, and RMSE for continuous skills. By the end of Part 1, you should be able to look at any outcome measurement and say exactly what question it answers, and when bias and consistency need to be teased apart. Here's the organizing idea for the whole chapter. There are many ways to measure motor performance. Table 2.1 in your textbook lists dozens, but they all fall into 2 big buckets. On the left, performance outcome measures. These tell us about the result of performance. Did the goal happen? How fast was the mile? How many free throws went in? How high was the jump? How long did the patient hold the stork stance? Notice what these measures don't tell you. They say nothing about which muscles fired, which joints rotated, or how the limbs were coordinated. They only describe the outcome. On the right, performance production measures. These tell us about how the body produced that outcome, what the limbs, joints, and muscles were actually doing. Limb displacement, joint angles at impact, knee torque, EMG patterns, brain activity. Production measures map directly to the movement and neuromotor levels of analysis from Chapter 1. Outcome measures map to the action level. 2 categories, 3 levels, same conceptual world. The choice between them is a choice about what kind of question you're asking. If your PE student missed the basket, the outcome measure is the score. But if you want to know why she missed, you need production measures. Was her elbow too low? Was her wrist snap mistimed? Outcome answers what? Production answers why. Reaction time. The interval of time between the onset of a stimulus signal, the go, and the initiation of the movement. Look at the diagram. First, the warning signal gives the performer a heads up. Then comes the 4 period. A deliberately variable wait so the participant can't anticipate the go. Then the go signal fires. The interval between the go and the first observable movement is reaction time, RT. The interval between the start of the movement and its end is movement time, MT. And the entire interval from go to movement complete is response time. Sometimes confusing, because in everyday speech we'd call all of that just reaction time. In this course, response time is the sum. 2 non-obvious things to remember. First, RT does not include any movement at all. It ends the instant the limb starts moving. Second, RT and MT are independent. The fastest reactor in your group isn't necessarily the fastest mover, and vice versa. This matters in the real world. Imagine a football lineman is consistently slow off the snap. 2 possible reasons. 1, he's not paying attention to the snap, so his RT is too long. 2, he reacts fine, but his foot is slow off the ground, so his MT is too long. Same outcome, completely different coaching intervention. Or in driving rehab, if a patient is slow to brake when something appears in the road, an extended RT means decision-making is the problem, and you train attention. And extended MT means movement speed is the problem, and you train leg strength and execution. Now, objective 2, the 3 types of RT. They differ in how many signals there are and how many responses are required. Simple RT, 1 signal, 1 response. You see a light come on, you lift your finger. A sprinter at the starting blocks listening for the gun. This is the fastest RT situation because there's nothing to decide. Choice RT, many signals, and each signal has its own response. Red light equals lift index finger. Blue light equals lift middle finger. Green light equals lift ring finger. In the real world, a driver at an intersection. Red means stop, yellow means prepare to stop, green means go. 3 signals, 3 different responses. Choice RT is the slowest because the brain has to identify the signal and select the right response. Discrimination RT, many signals, but only 1 response to only 1 specific signal. Red light equals lift finger. Blue or green do nothing. In the real world, a jogger scanning the path ahead. Many things in the visual field, only a specific kind. A curb, a tree root, an obstacle triggers the step-up response. Leaves, shadows, dappled light, those get ignored. So when you're designing a practice or an assessment, ask yourself which RT situation it is. A goalkeeper facing a penalty kick is a discrimination task. Many cues, but only certain ones predict ball direction. A multiple choice driving test is a choice task. Different signs require different actions. A reflex hammer test? Effectively a simple task.
Now, for an elegant little technique, fractionating RT. Remember, RT is the interval from the go signal to the start of observable movement. If we put an EMG electrode on the muscle, we discover that this interval has 2 parts. The first part, premotor time, is the quiet interval from the go signal until the muscle actually shows electrical activity. Look at the EMG trace in the diagram. The line is flat, 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 and then it starts firing. The time from the go to that moment of firing is premotor. It's the time the nervous system needs to receive the sensory information, process it, decide what to do, and send the command down to the muscle. Premotor time is essentially a measure of perceptual and cognitive activity. The second part, motor time, is the interval from when the muscle starts firing until the limb actually moves. There's always a lag here because the muscle takes time to overcome the inertia of the limb. The motor time is the mechanical, physical part of getting the limb moving. So premotor plus motor equals RT. Why split it? Same diagnostic logic as RT versus MT. If a stroke patient has a slow RT, fractionating it tells you whether the delay is in the nervous system decision-making part, premotor, or in the muscle's ability to get the limb going, motor. In the football lineman example again, extended premotor time means he's not attending to the snap. Extended motor time means his muscles can't fire fast enough to overcome the inertia of his crouching body. Different problem, different intervention.
3 error scores for one-dimension skills, and the critical thing is that each one answers a different question. AE, absolute error, is the unsigned deviation from the goal. If the target is a 50-centimeter stride and the patient took a 65-centimeter stride, AE is 15. If they took a 35-centimeter stride, AE is still 15. AE tells you the magnitude of the error, how far off, on average, regardless of direction. CE, constant error, is the signed deviation. Now 65 versus 35 are different things. 65 is plus 15, 35 is minus 15. Average CE over a series of trials tells you whether the learner has a directional bias. Are they consistently overshooting or undershooting? VE, variable error, is the standard deviation of the CE scores. It tells you how consistent the performance is. A low VE means tight, repeatable performances. A high VE means scattered, unpredictable performances. Here's why all 3 matter. Look at the box at the bottom, the Joe and Sam example from the textbook. Both Joe and Sam are physical therapy patients working on stride length with a 50-centimeter target. Both have the same AE, 11 centimeters, identical magnitude of error. But Joe has a high negative CE, minus 11, and a low VE, about 3. That means Joe is consistently short. He has the basic pattern, he just hasn't yet scaled it up to a full 50-centimeter stride. Your intervention with Joe? Cue him to push off harder. Give him a target line on the floor. Build in confidence. Sam, on the other hand, has a low CE, about 3, but a high VE, about 12. Sam is sometimes long, sometimes short, sometimes way long, sometimes way short. He doesn't yet have a stable pattern. Your intervention with Sam? Lots of repetitions on the basic stride, with knowledge of results every trial to build a reliable movement pattern. Same magnitude of error, completely different problems, completely different rehab plans. This is the single most important practical idea in the whole chapter. Don't just measure how much someone missed, measure how they missed.
Two-dimension errors. Sometimes the learner can miss in 2 directions at once. A dart can miss left or right and high or low. A golf putt can miss left or right and short or long. Now the one-dimension trick of subtracting from a target doesn't work. You have 2 distances. Radial error, RE, is the 2D version of AE. Look at the dart example in your textbook. Measure the X miss, square it. Measure the Y miss, square it. Add them, take the square root. That's the Pythagorean distance from the target to where the dart landed. That's RE. For an average RE across multiple trials, just average the trial REs. Now, what about bias and consistency in 2 dimensions? The signed math gets complicated. You can't just add plus 15x with minus 15y. So in 2D, we mostly use a qualitative assessment. Look at the grouping of the shots. Look at golfer A and golfer B in the diagram. Both putted 6 balls. Both have 1 putt in the hole. Golfer A has the other 5 balls scattered all around the hole, a consistency problem, high VE. She doesn't yet have a stable stroke pattern. Golfer B has the other 5 balls grouped tightly to the right of the hole, a bias problem, high CE. She has a great stroke, she just doesn't have it aimed right. Same overall accuracy, 2 completely different coaching priorities. For golfer A, you take her to the practice green and work on basic stroke mechanics. For golfer B, you just change her aim by half a degree and watch her drop putts. 5 minutes of work for golfer B, 5 weeks of work for golfer A. Diagnose first. And then continuous skills. Walking a line, steering a car, tracking a cursor with a joystick. The goal here isn't to hit a single target, but to stay on a continuous pathway. So our error measures have to compare the learner's whole trajectory to the whole target trajectory. The most common is root mean squared error, RMSE. Think of it as AE for tracking tasks. A computer samples the target's position and the learner's position many times per second. Say 100 hertz, 100 samples per second. If the trial is 5 seconds long, you have 500 paired position values. At each pair, you take the difference, the moment-by-moment error. You square those differences, average them, take the square root. That's RMSE. Look at the chart on the right. The solid line is the target trajectory, the path you wanted the learner to follow. The dashed line is the learner's actual trajectory. The little vertical ticks are sampled errors. RMSE collapses all those errors into one number that you can track across trials, across days, across rehab sessions. For a PT working with a patient on a treadmill mounted with a video screen, or a driving instructor working with a teen in a simulator, RMSE is the right tool. As an instructor, your principle is the same as before. Pick the measure that matches the shape of the skill. Discrete one-dimension goals get AE, CE, VE. Discrete two-dimension goals get RE plus visual grouping. Continuous skills get RMSE.
Pulling part 1 together. Outcome measures in one mini lecture. First, the 2-category framework. Outcome, the result, versus production, how the body got there, mapped onto the 3 levels of analysis from Chapter 1. Second, reaction time. 3 flavors: simple, choice, discrimination, measuring different cognitive loads. Plus fractionation, splitting RT into premotor, the thinking half, and motor, the moving half. Third, the error family. AE for magnitude, CE for direction, VE for consistency in one dimension. RE plus a qualitative read of the shot grouping for 2 dimensions. RMSE for continuous tracking. The italics at the bottom is the line I want you to take into the rest of the chapter. Bias versus consistency. 2 learners can post identical AE scores with completely different problems and completely different interventions. Don't just measure how much someone missed,
measure how they miss. Diagnose the shape of the miss, not just its size. Part 2 next.